Hi, I'm Dr. O. Today I would like to share with you a practical example of reinforced concrete beam design. If you have any questions on this video, you may reach me through this email. These are the two references used for the content in the video. Here, a Flexural design for reinforced concrete beam in Greek. A to D is shown. There are few design inputs or parameters listed here. The dimensions, the span, the width, thickness, size, the actions, GK, QK, and the material parameters, unit weight, characteristic strength of concrete and steels, and also the nominal concrete cover. This video only shows the practical solution to Flexural design according to Eurocode 2, which is also ultimate limit state design. This is a design procedure for rectangular section. Definition for symbol B, H, D, X, D prime, Z, you can find from figure 2.2. The derivations for the equations are not the scope of this video. This is the design procedure for flange section. Effective flange width for this problem can be determined by referring to clause 5.3.2.1. Structure analysis of the continuous beam to be carried out once the design actions were determined. The bending moments and shear force for this problem can be obtained from table 3.14 PS at 110, part 1, 1997, confirming the requirements such as this is a continuous beam with equal spans, with uniform action, and the QK is less than GK. Maximum moments at several locations need to be obtained, such as the sagging moments at the midspan, AB, BC, and CD, and also the hogging moments at the support B and support C. Now we can start with Flexural design. For span AB and CD, the applied moment is 194 kN/meter. We will start with calculating the MF. Then we compare the M and the MF. MF can be obtained from this equation, which requires the FCK, B, HF, and D. For these sections, the BF will be used, the effective flange width, 2,140 mm. Now, once we know that M is less than MF, we have to follow the several steps here by calculating the K, the Z, and later AS. You need to know that the limiting value for Z is 0.95T. If you obtain Z is greater than 0.95T, you will use 0.95T. This is the AS required for these sections. From this equation, you obtain 1,081 mm squared. So you need to provide what we call an AS provided greater than this amount. You can use this table. Probably you are asking how to get this value in the table. This is the cross-sectional area for the diameter bars at mm. To get this value, we use pi d squared over 4. Pi multiply h squared divided by 4. Similarly, you can obtain 5 numbers of H20. You need to make sure that AS provided is greater than AS required. Similar Flexural design procedure is applicable for span BC. So for support B and C, we deal with the negative bending moment or hogging moment. In this case, the beam behaves like a rectangular section, which the flange now is in tension, and it makes no contribution to the flexural strength of the section. Therefore, when we are applying the B in this procedure, B web will be used. So we start with looking at the applied moment. Then we calculate the K using this equation. Then we calculate the K balance. If you look at, there is a delta in these equations. If you do not apply any moment redistribution to your analysis or design, so the delta will be 1 and the K balance will be always 0.167. So you have to compare the K and the K balance. If the K and K balance, K is less than K balance, compression reinforcement is not required. But if K is greater than K balance, or in this case, K is more than K balance, the compression reinforcement is required. Then you need to follow these following steps. You need to determine the Z, the X, using these equations, and then determining the compression reinforcements, AS prime, then later the AS, the tension reinforcement. If you look here, there is a ratio D prime over X. To note, if ratio D prime over X is less than 0.38, the compression reinforcement can be assumed to reach the design strength 0.87 FYK. But if D prime over X exceeds 0.38, a reduced stress should be used. Therefore, there are two different equations, okay, to determine the AS prime. Now you have obtained the AS prime, area of compression steel, and AS, the area of tension steel. So you need to provide accordingly the AS provided. Remember, for the support, if you look at this moment, this is the hogging moment. So now the tension is at the flange or at the top part of your section. Therefore, the tensional steel that you provided should be placed at this location. And the compression steel will be placed at the bottom of the beam for support B and C. AS provided shall be checked against the minimum and maximum reinforcement recommended in 9.2.1.1. So these are the equations used to determine the AS minimum, and it need to be more than 0.0013 BD, and AS maximum 4% of the cross-sectional area of the section. Remember, in this case, the B, we will use the B web. And FCTM can be determined from table 3.1, Eurocode 2, part 1, 1. For this case, if we have a FCK of 25, so the FCTM is 2.6. This is the detailing of the problem based on the flexural design. We can use the source, the guideline from how to design concrete structure using Eurocode by the Concrete Center. So if you look at, we are providing 100% of the AS provided at the midspan, when it can be reduced to 30% at the distance away from the support. And if you look at the support, we have provide 100% AS provided here, and it can be reduced to 60% and 35% away from the supports. So look at our detailing for beam 1A, A to D. So 5H20 is 100%. When come to near the supports, it have reduced to 30%, 3H20. At the support, we have 5H20 AS, and the AS prime is 3H20. And at the distance away, we can reduce to 60% and come to 35%. We provide 2H16. The detailing can be shown in elevation and also the cut section. If you look at, I have highlighted the AS provided for the midspan AB 5H20. So 5H20 can be placed in 2 layers. Therefore, in the elevation, you need to draw 2 lines. For the supports, AS is 5H20, AS prime is 3H20. So here at the support B, we have 2 layer 5H20, means 3H20 plus 2H20, and the AS prime is 3H20. So come to midspan BC, we have 3H20 here. Another important note for detailing is the anchorage and lap length. Here I show how to determine the lap length when one need to lap the reinforcement. Choose a typical value depending either good or poor bond condition. Say in this case, it is poor bonding condition. So if we want to have this determine the lapping length, the lap length here. So we look at the detailing here. We have bar H16 and bar H20 lapped together. So we need to use the value obtained from the table 66, and we multiply with a smaller diameter between these lapping reinforcement. Then it will be 16. Therefore, you get 1060 mm. I end my video on flexural design for RC beam. See you in my next video.